Hey guys, so today we're working on the LONCAPA video solution for the merry-go-round problem from problem set 5. The question reads, a child sits on a fiberglass mousse fastened 9 meters from the center of a merry-go-round platform that is rotating once every 15 seconds. What is the child's speed while sitting on the mousse? Alright, so I'm going to start off by drawing a picture and just going over some conceptual stuff when it comes to circular motion. It's not necessarily needed for this problem if you already have a background in it, but just to get some basics down. So we're going to start by drawing the merry-go-round platform, which obviously is a circle. We're working with circular motion. And we'll also just draw the center while we're at it. And we will label the radius, which is equal to 9 meters. They gave us that in the problem. And I'll just put the mousse here in yellow so we can see him better. Now, if I were to draw the motion of this mousse, then I could draw some velocity vectors. And so we'll start with v0, let's say like when he's here, then his velocity would be v1. When he's here, his velocity is going to be v2, and so on. And just what we could do with this, like if we were working conceptually, is we could draw this v0 vector, and we can do vector addition with the v1 vector. And so now from this point to this point, we can draw delta v. And the reason that that's important is because acceleration is the change in velocity over the change in time. So this is essentially our acceleration vector. And what that would mean is that for v0, the acceleration is pointing radially inward. And if we were to do that for each different position that the mousse is at, then we could draw all of these little acceleration vectors, and every single one of them is going to point in towards the center. This is centripetal acceleration, and they point radially inwards. So anyways, now let's actually get into the problem. We know that it rotates once every 15 seconds. So that means that the time that it takes to travel the circumference, which is equal to 2 pi times r, the time is going to be 15 seconds. And essentially, we can just take the circumference and divide by time, because velocity is equal to the change in position over change in time. Well, our position is 2 pi r minus 0 over t minus 0, which simplifies down to 2 pi r over t. So using that equation that we just derived, let's plug in some values. We have 2 pi times our radius of 9 meters divided by our time, which we said was 15 seconds. And this is going to come out with an answer of 3.770 meters per second. Yeah, so that's the answer for part 1. Moving on to part 2, what is the kid's acceleration while sitting on the mousse? Well, acceleration, it's change in velocity over change in time, but for centripetal acceleration, we're going to write it a little differently. I could take the steps right now to derive the equation, but just to save some time, we're going to take what's given, which is a sub c is equal to velocity squared over radius. Well, we already have velocity from part 1. That's what we just solved for. And we have the radius, which was given to us. So this makes this super, super simple. We're going to have 3.770 meters per second squared all over 9 meters. And this is going to give us a value of 1.58 meters per second squared. And that's our acceleration for part 2. Finally, we get to part 3, which is what is the child's acceleration if he moves to the rubber beaver fastened 7.6 meters from the center? Well, what we were at before, oh, that was very bad. What we were at before is we have this large circle, and it had a diameter with our moose at the end of 9 meters. And we're just going to bring that in. So let's make our beaver blue, and he's this new little spot right here. And let's draw his new route of movement. He's going to come like this. A little bit misshapen, but that's all right. So this is going to be at 7.6 meters. Well, let's just think conceptually for a moment. Obviously, we can tell that this circumference here is smaller than the outer circumference of a 9-meter radius. And we could calculate that. We could calculate the actual circumference. We're just not going to do that right now. But because it's a smaller circumference, well, let me start this part over. The merry-go-round is all one piece. So we know that this inner circle is not moving separately from this outer circle. So the total time for this merry-go-round to move is still going to be 15 seconds total. But since this beaver has a smaller distance to travel around the circle, this means that the time that it takes, yes, it's the same, but the distance is smaller, so it's moving slower. Because if it was traveling the same speed as this outer circle, if it was going the 3.770 meters per second, then by the time 15 seconds passed, it would have made a full lap and then some. Which means that when we're doing this problem, we can check that we're on the right track by saying the velocity has to be less than 3.770 meters per second. So let's solve to see if we're right. So from our first problem, we derived that our equation is going to be 2 pi r divided by time. The only difference here from the first problem is going to be our r value. So 2 pi times 7.6 meters all over 15 seconds. And this is going to give us a value of 3.18 meters per second. And we know that this is right and that we're on the right track because as you can see here, 3.18 is less than 3.77 meters per second. So check, we're good with that. And let me just put this in a box so we can kind of see where we are. All right. So now we are looking for the acceleration. So we found the speed, and the reason we did that is because we're going to need it, like in this equation up here. We need that velocity speed. So we're going to say a sub c is equal to v squared over r, and this gives us 3.18 meters per second, and let's square that, all over our new radius of 7.6 meters, and that gives us a final value of 1.333 meters per second squared. So that is how you do this merry-go-round problem. Again, we can check this final answer here, that our acceleration is less than the other acceleration, which obviously the moose has to be moving faster, so it'll have a higher acceleration. But yeah, so that was the merry-go-round problem. I hope this helped.